and welcome to this video on OCR A, Bonding and Structure. My name is Chris Harris and I'm from AlleryTutors.com, and in this video basically we're just going to go an overview of bonding and structure for OCR A. Now the slides I'm going to use here you can purchase. You can click on the link in the description box and you can get a hold of them there. Great for things like revision, supplement your revision notes that you've got in the books, etc. You can put these on your tablet, on your phone or anything like that, and you can look at them on the move. So they'll be ideal for that. Like I say, this thing this video, is specified to OCR A, and it kind of meets the spec points that have been listed on here, which have come from the OCR A specification. Okay, so let's make a start. Let's look at ionic bonding. Okay, so ionic compounds are basically they're oppositely charged ions, and they're held by these strong electrostatic attractions. So let's look at an example. Here's sodium, here's chlorine. Sodium has got one electron in its outer shell. It needs to lose that electron and to get a full shell. Chlorine needs to gain one to get a full shell. Okay, and basically they're going to form ions in the end, and they're going to attract to each other. So there it is, and there's your ion. So sodium and chloride ions. So sodium ion, which is positive, and chloride ion. So these two actually attract each other because they're oppositely charged. So looking at the periodic table, group 1s form 1+ ions, group 2s form 2 pluses, group 3s form 3 pluses. We get to group 5. These have 5 electrons in their outer shell, but it's easier for them to lose the 3 electrons than to gain 5. To lose 5. It's easier for them to gain 3, than to lose 5. Right, let's get this right. Okay, so 5 electrons in the outer shell, really difficult for them to lose them, so it gains the 3. So that's why it's got 3 minus ions. Same with group 6, they form 2 minus ions. Group 7s form 1 minus ions. Need to know your molecular ions. Hydroxides are OH minus, nitrates are NO3 minus, ammonium is NH4 plus, sulfates SO4 2 minus, carbonates CO3 2 minus. Make sure you know these molecular ions. They're really, really, really important. Okay, right. So we can work out the formula of ionic compounds by using something called a swap and drop method. So the first thing we need to do is to write our ions. There they are there, calcium and nitrate, Ca2 plus, NO3 minus. Swap the charges over, like we've done there, and drop the charges. So you can see here we've swapped the 2 plus and the minus over, drop them, in other words, get rid of the plus and the minus bit and keep the number bit, and drop them so they're lowercase like this. So Ca, NO3 in brackets with 2 of them, because we want both NO3s, we want the full part. And we simplified to the whole number ratio. So you can see here we've got calcium and nitrate. So this is already in the whole number ratio, so we don't need to do anything with it. Let's look at another example. Calcium, Ca2 plus and O2 minus. Write the ions down, swap the charges over, drop the charges, and then simplify. So Ca2O2 can be simplified to CaO, and that is the formula. That is calcium oxide. So ionic compounds like sodium chloride, these have giant ionic structures. So you can see here that we've got a giant ionic structure for Na plus and Cl minus ions, all arranged in this big cubic structure. So it's a regular structure, so we've got this pattern as you can see. Cubic, it's a cube shaped, and it's a giant repeating pattern because it's a large compound, all joined together. Most ionic compounds, they dissolve in water. Water's polar. There's a delta negative and a delta positive bit. The delta negative attracts to the positive sodium ions. The delta positive hydrogens are attracted to the negative chloride ions here. Basically, they pull this structure apart. They conduct electricity when they're molten and they're dissolved in solution. As the ions are free to move around, so when you dissolve these in water, the water breaks the structure up. Melting does the same as well. Free moving ions means they can conduct electricity. High melting points, lots of strong electrostatic forces between these ions here. Really important that you know that. Lots of energy is needed to overcome these forces. Anything underlined here is really important. You've got to mention it when they ask this question in the exam. So things like high melting points, it's a very common question for them to ask. Okay, let's look at another type of bonding, covalent bonding. So covalent bonding is basically the sharing of outer electrons, slightly different to ionic, where the electrons are literally donated and accepted. This is sharing, and basically they do that to get a full outer shell. And there's electrostatic attraction between these shared electrons in the positive nucleus, and this is what the covalent bond is. We get single, double, and triple bonds. Obviously, we've got more than one electron being shared. Sometimes we need to do that if we're going to get a full shell of electrons. And we can represent covalent bonds using these lines as well. This is a displayed formula of water. Dative covalent or coordinate bonds. This is where one atom donates 2 electrons to an atom or an ion to form a bond. Here's ammonia here. Lone pair of electrons on the ammonia. Hydrogen doesn't have any electrons. H plus doesn't have any electrons. So therefore it can't form a traditional covalent bond because it doesn't have any electrons to share. So both the electrons have to come from the nitrogen to the H plus ion. There it is. Look, sits neatly in there. This is a dative covalent bond. Both electrons are coming from the nitrogen to the H plus ion. We can also represent it using an arrow in the displayed form like this. So you can see we've got an arrow here. The arrow represents the coordinate bond or dative covalent. Both electrons are coming from the nitrogen to the hydrogen. That's why the arrow is pointing upwards. Make sure you're able to draw these properly. Okay, let's look at, as soon as we're looking at obviously covalent molecules, we're going to look at the shapes of molecules. So we're going to use bond pairs and lone pairs of electrons to work out the shape. So let's have a look at this one. This is an example. This is the one with 4 bond pairs. The reason why this has a very fixed shape, or molecules with 4 bond pairs has a very fixed shape, is because these bonds repel equally. They want to be as far away from each other as possible. Remember, they've got electrons in there. The electrons repel each other. They have a fixed bond angle as well. In this case, it's 109.5. But if you've got lone pairs on your molecules, these will repel more than 2 bond pairs together. So these 2 bond pairs will obviously repel. But if you had lone pairs in there, they'll repel further. And 2 lone pairs together will repel even further than that. So let's have a look at this one. 1 lone pair there. You can see it's forced the other 3 down closer towards each other. And now we've got a bond angle of 107 compared to 109.5 we had before. And 2 lone pairs squash it even further. And we've got to 104.5 now. So you can see that these 2 lone pairs are really repelling each other now. And it's squashing this bond angle close together. So lone pairs, what they do is they change the shape and bond angles. Lone pairs basically push the bonding pairs close together. Generally, for every lone pair of electrons that you add, you reduce the bond angles by 2.5 degrees. You can see here 109.5 minus 2.5 gives you 107. 107 minus 2.5 gives you 104.5. This doesn't apply to some molecules, but we'll look at them later on. So there's always exceptions. Okay, right. So let's have a look at some of these rules. So we're going to use bond pairs and lone pairs to work out the shapes of some of these molecules. So what we should do when we're trying to work these out is we should draw a dot cross diagram of what we've got, what they've asked you to work out. This way we can work out how many bond pairs and lone pairs they have. Now this is methane, it's neutral. Sometimes you get ones with charges on, you need to know what to do with them. So with ions, what we do is we add electrons to the central atom for negative ions, and for positive ions we remove them. So for example, ammonium, NH4+, the nitrogen would have 4 electrons. Normally nitrogen has 5 electrons, it's in group 5. Because it's got the positive charge, we remove the electron from the central atom, then work it out from there. Now I must add this setup here, this kind of process is only applicable for working out bond angles. This isn't actually what happens in reality. This is purely just a method for working out the bond angles. So if you look here, you've got bond pairs 4, lone pairs 0. This has got a total of 4. So this total number here, this basically tells you it's tetrahedral. We'll look at the shapes in a minute. If you have lone pairs though, you need to replace the bonds for the lone pairs and change the shape and the bond angle. Again, we'll look at some examples where you have lone pairs as well. So we've got one here. This one actually does have lone pairs, as you can see. This is water. 2 bond pairs, 2 lone pairs. Look at this. 2 bond pairs, 2 lone pairs. Totals 4. This is still based on a tetrahedral, so that'll be a starting point. So you start with 109.5 for a tetrahedral, and basically you shrink it by 2.5 degrees for every lone pair. 2 lone pairs here, so that shrinks by 5 degrees. This is the angle between the 2 bond pairs. Okay, so we're going to start by looking at shapes with no lone pairs first. Okay, so these have molecules with no lone pairs, and you need to know the shape of the molecules. You've got to remember these. So let's have a look at the first one. This has got 2 bond pairs and no lone pairs. An example is beryllium dichloride or beryllium chloride, BeCl2. This is a linear shape, 180 degrees between them. Make sure you remember that one. The next one, 3 bond pairs, no lone pairs. The name of this shape is trigonal planar. Again, the bond angle between this would be 120 degrees, as you can see on there. So make sure you know the name as trigonal planar. This is a flat molecule. It's got 3 bonds. So that's why it's called trigonal planar. Okay, the next one, 4 bond pairs, no lone pairs. These molecules are called tetrahedrals. And it's the first time we have a 3D shape. Dotted lines show bonds going away from you. Wedges show bonds coming towards you. Bond angle between each of these is 109.5. That's the furthest away they can get from each other. And first time we've got a 3D shape. Tetra meaning 4. Tetrahedral. Okay, the next one. This one's 5 bond pairs, no lone pairs. This is called trigonal bipyramidal. Again, look at the shape of it. We have 3. We have a triangle bit here in the middle. That's 120. It's basically just this tipped on its side. And then we have 2 polar groups, 2 polar atoms, top and bottom. The bond angle between the polar atoms and the trigonal planar bit is 90 degrees. Obviously, this is 120. Reason why we call it trigonal bipyramidal is because we've got the trigonal bit in the middle. And if I draw a line from this atom to this atom, and this atom to this atom, and that atom to that atom, we form a triangle, a pyramid shape on the top. If we do the same on the bottom, we get another pyramid. That's why we call it bipyramidal. Okay, bond pairs 6, lone pairs nil. Sounds like some kind of football score. An example is SF6. This is an octahedral shape. Be careful, this has got 6 bonds, not 8. Oct is normally for 8, but I'll tell you why it's octahedral. Bond angle is 90 degrees between everything in here. We have this square planar bit in the middle here, and we have the 2 polar bits, top and bottom. We call it octahedral. If I draw a line from here to here, here to here, here to here, and here to here, so we form a square, a 4-sided pyramid shape on the top. If we do the same on the bottom, we have another 4-sided pyramid shape. So because it's 4-sided on the top and bottom, total number of sides is 8. That's why we call it octahedral. Okay, let's have a look at them with no lone pairs. So again, same setup. So bond pairs 3, lone pairs 1. Example would be ammonia. The name of the shape is trigonal pyramidal. There it is there, look, 107 degrees this time. So we start at 109.5 for tetrahedral. Shrink it by 2.5 degrees, we get 107. Okay, 2 bond pairs and 2 lone pairs. Example is water here. This is called a bent molecule. Angles 104.5. Again, we've shrunk it by another 2.5 degrees because we've got 2 lone pairs. 3 bond pairs, 2 lone pairs. Trigonal planar is this example. So you can see we've got 2 lone pairs, top and bottom. We did have the 2 poles there. Now, this is one of the exceptions where the bond angle actually doesn't change. These lone pairs will squash these down further down. These lone pairs will push them back up again. So because they're acting equally, they kind of cancel each other out. So we have no effect on the actual bond angle. And finally, we have 4 bond pairs and 2 lone pairs. This is an example of a square planar. Again, this would have been based on an octahedral shape. Take the 2 poles out. We have 90 degrees that's left behind. And so we've just got this flat shape here. And this is called square planar. But like I say, the bond angle remains unchanged as the 2 lone pairs repel each other equally from opposite sides. Okay, let's have a look at electronegativity. So electronegativity is the ability for an atom to attract electrons towards itself in a covalent bond. Now basically, the further up and right you go in the periodic table, excluding the noble gases, the more electronegative the element is. So fluorine is the most electronegative element. We can measure this on something called a Pauling scale. This basically helps us to quantify how electronegative an element is. Fluorine is the most electronegative element. It has a value of 4.0. And then everything else is obviously going to be lower than that because they're less electronegative. And it's important to note as well that actually, if we look at the differences between them, we're looking at, say, for example, if I had hydrogen and fluorine bonded together, obviously there's a big difference in electronegativity values, so 2.2 and 4. Basically, the bigger the difference, the more ionic the compound's going to be. That's quite important. But a difference of 0 will be purely covalent. So an example could be Cl2. So 2 chlorines put together, no change in the electronegativity value. So that would be purely covalent molecule. Okay, so look at some polar bonds then. So covalent bonds can become polar. If the atoms attached to it, they have a difference in electronegativity. The bigger the difference, the more polar the bond will be. So if you have a look at this example here, hydrogen and chlorine, delta positive on the hydrogen, delta negative on the chlorine. Basically, the chlorine's more electronegative. It's pulling electrons towards itself in this covalent bond, and that's why the electrons sit to the right. So to show this polarity, we'll put a delta positive next to the least electronegative element. In this case, it's hydrogen. Delta negative next to the most electronegative is chlorine. This is basically showing us that we have a polar bond. Some molecules like this, for example, are not polar. They are both just as electronegative as each other, so therefore the electrons sit bang in the middle between them. Also, hydrocarbons are not classed as polar too. Basically, even though we've got a slight electronegativity difference between carbon and hydrogen, because it's really, really small, we class hydrocarbons as non-polar. Some molecules, like water, are also polar. We've got an uneven distribution of charge. So basically we get water which is not polar, but just be careful for some molecules which may look as though they're polar, but because the charge is distributed evenly in this molecule, like carbon dioxide, we have a symmetrical arrangement, therefore we have no overall polarity in this molecule. Okay, let's look at some intermolecular forces. We're going to look at induced dipole-dipoles first, also known as London forces. Now these exist between atoms and molecules. They are the weakest out of the three, which we're going to look at. Basically, any molecule or atom that has electrons can form a dipole when they move near to another atom or molecule. That's why we call it an induced dipole-dipole. So here's a setup here, delta positive, delta negative on our molecule. Basically, we get the shifting of electrons in this molecule. They move to one end, and we create a temporary dipole. Now, they'll only do this when they come in contact with another molecule. Okay, so that's really important when they're nearby. So when they move away, this interaction is destroyed. So let's have a look how they interact. There it is there, look. You can see the delta negative on this side of the molecule will interact with the delta positive on the other. So the electrons moving up to this side of the molecule will shove the electrons on this molecule over to one side, and so on. And you can see we've got these little kind of delta negative positive attractions here, but this is only there when these molecules are nearby. As soon as this molecule leaves or moves somewhere else, the electrons will then nudge back over. Obviously, we need to know this and apply this, and we can apply it to crystal structures, such as iodine, as an example. Here's the setup for iodine. Here's some iodine crystals. Make sure you know that we have weak induced dipole-dipole forces holding these iodine molecules together, but we have strong covalent bonds that hold the atoms together. Okay, make sure you know the difference. Intermolecular means between molecules. So basically, the bigger the molecule or the atom, the more induced dipole-dipole forces you get, and you have larger electron clouds. This is the reason why we have larger induced dipole-dipoles. And remember, when we boil a liquid or even melt this, well, actually we sublime iodine, but when we heat it up, all we're doing is breaking the weak induced dipole-dipole forces. We're not breaking covalent bonds. Covalent bonds take so much energy to break. So when we boil water, for example, and we turn it to steam, the only thing we're doing is we're heating it to break or weaken them forces between the molecules. Okay, we must have enough energy, obviously, to overcome these forces as well. Hydrocarbons also have these induced dipole-dipoles, but the longer the hydrocarbon, the more induced dipole-dipole forces you have, and hence the higher the boiling point, because we need more energy to overcome these forces. Again, the molecule's longer, it has more electrons, so therefore it'll have more induced dipole-dipoles. Branched hydrocarbons, these do the same. Basically, these means that the hydrocarbon chains can't pack closely together. This means that the surface contact between the molecules is not as great, weakens the induced dipole-dipole force between the chains, and lowers the boiling point. So branching lowers the boiling point of the hydrocarbon. Very important that you need to know that. Okay, let's look at the next strongest one. These are dipole-dipoles, or permanent dipole-dipoles as they're known as. So these, as the name suggests, are molecules where they have this permanent dipole instead of an induced one. So, for example, HCl is an example of this, delta positive, delta negative. So these exist when we have a permanent polarity, not an induced one. So we've got a weak electrostatic force between a delta negative chlorine and a delta positive hydrogen. The delta negative part on one molecule is attracted to the delta positive on another. And unlike the induced dipole-dipole forces, these permanent dipole-dipoles are involved in molecules with a permanent dipole, and these are stronger. Make sure you mention the word dipole-dipole. You can't just put permanent dipole. You have to mention it twice. okay, because you've got two dipoles here, two molecules. Okay, so these are stronger than your induced dipole-dipoles. Really important to know though, just because it's got a permanent dipole-dipole, it also has an induced dipole-dipole as well. So it doesn't mean that you just have that one, you actually have both of them. It just means the strongest one is a permanent dipole-dipole. Too many dipoles here, I think. Right, we can test these polar molecules really easily. If we take the polar molecule, run it through a burette, and you get a thin stream, steady stream of this polar molecule. If you place a charged rod near it, what should happen is it should bend towards the rod. So basically the polar molecules will align themselves against this positively charged rod in this case, the negative delta negative oxygen, the line all align, and basically the water will bend towards this rod. Okay, so make sure you know that this is a test for polar molecules. Okay, the strongest type of intermolecular force is a hydrogen bond. Now, hydrogen bond, even though it's got the word bond in, it is still a force, but it's the strongest one. These only occur when you have an interaction between hydrogen, obviously, and the three most electronegative elements. So, obviously, we've got hydrogen there, and the three most electronegative elements are NOF. N, O, and F, nitrogen, oxygen, fluorine. So when you're looking for molecules, any molecules that have a hydrogen in and either N, O, or F, you will get some hydrogen bonding. So we can show this using this diagram here. You can see we've got some water molecules set up. Hydrogen bonding is an interaction between the lone pair of electrons on an atom and a hydrogen on another atom. Okay, so you can see here, this is an example of water. Make sure when you're drawing these that you put all your partial charges on there, delta positives, delta negatives, lone pairs, interaction with a delta positive hydrogen on another molecule. Make sure you show all of these. It's really important. Very often they ask for the whole lot, so make sure you can do it. And also, just like with all the other ones as well, if a molecule has hydrogen bonding, it also has permanent dipole-dipoles and induced dipole-dipoles as well. So it doesn't just have hydrogen bonding, it has all three. So let's look at this weird phenomenon. This is to do with ice. Now, ice is strange because when you take water and you freeze it, it actually gets bigger, it expands, it becomes less dense. Now, normally with most materials, when you cool a material down, it contracts, it gets smaller, but ice is different. And this is actually all down to the hydrogen bonds. They push these water molecules apart in the crystal. Okay, so you can see here, it forms this regular structure. There's your hydrogen bond in between the water molecules in the ice, makes it less dense, and obviously the ice floats on water. And obviously you'll know that because you would have seen it yourself. And we can obviously compare boiling points and use these intermolecular forces to kind of compare them. Now if we look here, HF, this has the strongest type of intermolecular force. This is hydrogen bonding. Much more energy is needed to overcome these electrostatic forces of attraction between the HF molecules. Make sure you can comment on that, and this is the why HF is obviously higher. HCl doesn't have hydrogen bonding. The strongest it's got is permanent dipole-dipole, so therefore its boiling point reduces quite significantly. But then it starts to rise, as you can see here. The reason why is because actually we have much more electrons in here, bigger molecules, more induced dipole-dipole forces between HBr and HI and HCl. So you get this gradual increase. Make sure you can comment on this in terms of induced dipole-dipole forces. Okay, let's look at a summary, basically, just finally, of the types of bonding that we've seen so far. Simple molecular or simple covalent, iodine, ammonia, water are an example of that. Normally liquids are gases at room temperature. They don't conduct electricity when they're solids or liquids. Soluble in water depends on the polarity of the molecule. If it's polar, it will dissolve in water. If it's not polar, it won't. Melting boiling point, it's low. You're breaking weak forces, so we're not breaking any bonds here, so that means it's low melting boiling point. Giant ionic, things like sodium chloride, calcium oxide, magnesium bromide, look for metals and non-metals. They're solid at room temperature and pressure. They don't conduct when they're solid because the ions aren't free to move around, but they do when they're a liquid. They do dissolve in water because water's polar and the obviously ionic compounds dissolve in polar solvents. And melting boiling point, very high. This time we're talking about strong electrostatic forces between oppositely charged ions. Basically, we're having to break an ionic bond. It requires so much energy to do that. And yes, look at the solubility. The polar molecules, they do dissolve well in polar solvents. Non-polar molecules, like hydrocarbons, they don't dissolve. very well, in fact, poorly in water, because for something to dissolve in water itself has to be polar or has to be an ionic compound. And that's it. That's a summary of the OCR A of bonding and structure. I hope that was pretty useful. And please subscribe to the channel. Your support is much appreciated. Just click on the central button there in the circle. And if you'd like to purchase these slides for your revision purposes, then please click on the link in the description box. But that's it. Bye bye.